Hi everyone, Mrs. Patel Dane here for Galvanic and Electrolytic cells. So if you're watching this video before we've done the lab, please, I beg of you, do not kill the wonder for everyone else in the class. I want to make sure that everyone has an equal opportunity to be as successful as possible and to think. And if you've gone ahead and watched this, then that gives you an unfair advantage and also prevents other people from being able to be as successful as possible. So for this unit, or for this little lesson, excuse me, we are talking about electrochemical cells. So electrochemical cells mean that we have electrons flowing all around, and that might produce electricity or require electricity. So the first type of cell that we're looking at right here is called a galvanic or a voltaic cell. So this is important because we tend to say that this is essentially what is a battery. So this is a battery. That marker is no longer going to be used. Tossing that one away. So this is a battery, a much smaller scale version of everything that you might use in your life that contains a battery, but this is the science behind it. So we have a few things in our galvanic or voltaic cell. So one thing we might have is the electrodes. So two electrodes that I might be using right here would be copper and zinc. And these are just pieces of metal. Some other things I might have here are some solutions. So this would be maybe 1.0 molar copper sulfate. And in solution, an aqueous solution, excuse me, copper sulfate will be soluble in water. So I have Cu plus 2 and SO4 minus 2 in solution. And over here, I have 1.0 molar ZnSO4. So here I have Zn plus 2 and SO4 minus 2. These were both chosen for solutions because they are soluble in water. We want to make sure that they're able to be dissolved. So some new things that you might be seeing in here, or some reminders. Make sure that you know how to assign oxidation numbers to our elements and our ions. This is a review of topic maybe 4.9. So go back to unit 4 and topic 4.9 to review how to assign oxidation numbers. So these need to have a complete circuit, essentially. So inside of here, we have something called the salt bridge. So this salt bridge might just be a simple piece of paper that's been soaked in something like potassium nitrate. So potassium nitrate was chosen because it breaks up into K plus and NO3 minus. And I'll put a little note here. Choose a salt bridge that forms aqueous solutions. With your other solutions, i.e. it's not going to form a precipitate. We also want to have something that is ionic. So remember, all salts are called ionic, all ionics are called salts. So we want to make sure that we have an ionic substance in here. And the potassium ion will go in one direction and the nitrate ion will go in another direction, and we won't know that until we know what's happening into the individual solutions. So some other stuff to finish up our diagram here. We might have something in the middle, like a voltmeter or multimeter, and wires connecting them. This also might be, you might say like a clock or a light bulb or something like that. Because remember, what we're doing is creating a battery. So we're trying to show how electrons are flowing and how electricity is being produced as a result of that electron flow. Some other stuff that we know that we are going to be introduced to. So one is reduction potentials. So reduction potentials are pretty much a long list of what happens to these substances in a solution. So essentially, if I have copper plus 2 ions, they're going to add in 2 electrons to produce copper atoms that are solid. Whereas zinc, its reduction will do Zn plus 2 electrons will produce Zn 0 solid. And remember, anytime you have an ion, that's an aqueous solution. So every ion is an aqueous solution. So this is reduction because we have electrons in the reactants. Electrons are being added to the reactant to produce the product at the end. So these are called reduction reactions. We also have something called E cell values. Whoopsies, wrong color. Okay, E cell values are pretty much the electricity that's flowing or that can be potentially flowing from this reaction. So this is going to be equal to 0.34 volts, and this is a known, or this would be given to you. So you're never going to have to memorize any of these. So the electricity for a zinc solution would be negative 0.76 volts. So this is showing you what's happening when it's undergoing reduction. So in every reaction, if you can remember back to Unit 4, any oxidation reduction reaction will have reduction as well as oxidation. So reduction means that your electrons are in the reactants. Oxidation means that those electrons are being lost in the product. So for every one, you have to have the other. For us to figure out which one's going to undergo oxidation and which one's going to undergo reduction, there's two different ways. So one is if you have these E cell values, the more positive it is, it's undergoing reduction. So because we've got these two values, this one is more positive, it's undergoing reduction. This one, on the other hand, is going to undergo oxidation. So we will have to flip this equation. So instead of being like this, let's see if I can get myself some more space. I'm going to just put it over here. I'm going to flip the equation so that zinc solid produces zinc plus 2 aqueous plus 2 electrons. And get rid of that. So again, the some other little notes. The more negative, I need new markers. The more negative E cell value is oxidation, or at the anode. And the more positive E cell is reduction / the cathode. So that's how I figured out this one. On the Regents exam, you will not be given E cell values. Instead, you will be given your New York State reference table, Table J. And so I want you to dig this out right now because we're going to do both at this point. Obviously, you will not get this on the AP exam or the CAP exam, but it is nice to be able to have that. Just so that way you, just so that you have it. All right, so Table J. The elements towards the top on Table J are going to undergo oxidation. And oxidation, the anode, is the site of oxidation. Whereas towards the bottom, this is undergoing reduction, and this is at the cathode. So if we're comparing copper and zinc, copper is here, zinc is here. Copper is going to undergo reduction, zinc is going to undergo oxidation. Some things to help you remember this. A comes before C. So the anode comes before the cathode. I'm sorry I have to go up and down constantly for this. I'm sorry. So to remind yourself for reduction, the electron is in the reactants. And for oxidation, the electron is in the product. And we say that electrons are lost In oxidation and in reduction, electrons are gained. All right, cool. So that's one way if you were on the Regents to be able to figure that out. So let's talk about oxidation and reduction just for a little bit more on this. Some things to remember with reduction, again, electrons, if we go gain electrons is reduction. That kind of spells out GER. And if we lose electrons, that's oxidation. So we have a cute little saying that Leo, the lion, goes grr. And that kind of helps you remember which one loses electrons versus which one gains electrons. Some other things to help you remember the site of oxidation versus reduction. For reduction, we say this is red cat. So red stands for reduction at the cathode. So red cat versus the anode is the site of oxidation. So NOx helps us remember anode is the site of oxidation, and the red cat helps us remember that the cathode is the site of reduction. All right, a lot of stuff to remember here. So let's take care of figuring out if this is going to be spontaneous or not. So essentially, spoiler, this is supposed to be spontaneous. So if it's not spontaneous, it's not going to work. So let's calculate some values over here to ensure that this indeed is going to be spontaneous. So we say that we are going to figure out the E cell potential, and that is equal to the cathode minus the E cell for the anode. Now some notes. Yes, I did flip this equation. For this particular formula, I am not flipping the sign. However, you might use another formula which says the E for the oxidation plus the E for the reduction. In that case, yes, you would flip the sign for that E cell value for the oxidation, if that were the case. But I like to use this one because I can just use the values straight up and not have to remember which ones were flipped. So the cathode, that is going to be the site of reduction. So that is 0.34 volts minus the anode, which is my negative 0.76 volts. So essentially, those two negatives become a positive, and you end up with 1.10 volts total. This is good. If we have a positive E cell, this means it's thermodynamically favorable, versus a negative E cell is not thermodynamically favorable. Some other stuff to make sure we make a note of here. The electrons flow from the anode to the cathode. So this is our anode, this is our cathode. The electrons are flowing from our anode to the cathode, but through the wire. So we will have electrons go this way. So this means that this electrode, this piece of metal, is going to be negatively charged. If it's negatively charged, it's going to attract these ions, and those ions will then essentially gain those electrons and become a solid over here. So I can try to show you some really cool images. I think there's some other good ones online. I'm just trying to find like the best one. But essentially, right here we have copper atoms. We also have some electrons. These copper ions are going to be attracted to that electron and then form more atoms. So again, another copper ion might be attracted to that electron and form more atoms. So over time, the mass of your cathode should increase. So it should essentially be coated with more and more and more of whatever was in that solution. Conversely, over here, because electrons are leaving this electrode, that means that when you had zinc atoms, we'll just do this, zinc atoms on this electrode, like, let me show you that way, right? These zinc atoms are then losing an electron and therefore becoming a zinc ion in solution. So again, this is going to lose an electron and become a zinc ion in solution. So only atoms are going to be solid, ions are aqueous. So over time, if we let the cell run, we're going to lose mass on this side of that electrode or for that electrode. All right, so those are the two things there. One thing, oh yeah, so what ends up happening is that because this area tends to be more negative and this one tends to be more positive, our ions from the salt bridge are going to be attracted to one side of the cell versus another. So essentially, because you've got these ions, K plus and NO3 minus all hanging out in here, because this side ends up being more negative, your K plus kind of goes down here and your NO3 minus goes into that solution. So this cell will continue to operate until maybe until the zinc electrode disintegrates, maybe until these copper ions are exhausted, meaning that those copper ions have plated this entire copper electrode and there's no more of those in there. And what would more likely happen is that this potassium ion would come down here and then be attracted and then get coated onto here. So the main thing would be that salt bridge kind of runs out or maybe dries out. So there's a lot of stuff that might be happening in here that might exhaust the cell. So if we're thinking about like why do batteries run out or like quote unquote die, it's because we're exhausting some of the ions in the solutions. All right, so we want to put these two mini subcells together into one larger equation. So I'm going to calm down here. And I know that I have Cu plus 2. Ooh, we're going to have all the colors today. Plus Zn solid. Remember, that's a 0 because it's a neutral atom. All right, this is aqueous. And then that produces Cu solid on the electrode. That's a 0 charge. And it produces zinc ions in solution. That's a plus 2 charge. So yeah, there's a lot of stuff on this. What you did in lab was amazing. And what our batteries do every single day is amazing. One thing to make note here, this video, this is if you had the electronic version, my bad. But watch this video. It's a catchy little song that is really helpful when it comes to remembering what's happening in each of those cells. So what's happening for the anode and then what's happening for the cathode. All right, coming over here, moving on to the next one. So that one takes a lot. So my apologies. But this time we're dealing with the electrolytic cell. So the electrolytic cell is when we might be copper plating a nickel. So in here, I might have a nickel electrode that's solid, and I might have like a nickel coin. And using my markers. Okay, cool. So here we're going to have wires coming to them, and this time we're going to have a battery. So this battery is going to be responsible for helping us make this reaction occur. So this is originally a non-spontaneous reaction that we're forcing to actually occur. In the solution, I'm going to use the pink like I did before. We have Cu plus 2 and SO4 minus 2 in solution. So essentially, this nickel electrode, this nickel coin is what we want to plate with some of these copper atoms. So this side has to be negative. For this to be negative, I'll take a look over here. We have those copper ions from solution. They're gaining electrons to become copper atoms on that point. Conversely, over here, this nickel started off as a solid. It likely lost 2 electrons to become nickel plus 2 in solution. So over time, this solution will essentially run out of copper and be replaced with all nickel instead. So this side is negative, this side is positive. Electrons still flow from the anode to the cathode. So we have to think about which one is which. Let's see, I'm sorry. I know I'm moving all over the place here. This is undergoing reduction because my electrons are in the reactants. So this is the site of my cathode. Over here, this is undergoing oxidation. So this is my anode. So again, electrons are flowing from the anode over to the cathode. And that same thing happens for each one of them. Trying to think if there's anything else on this one that you might need to know. The mass of the nickel coin will increase. The mass of this nickel electrode will decrease. Trying to think if that's it for this one. And again, this is not spontaneous. So this will require electricity to happen, hence why you need that battery for this to occur. All right, and then we got this page. So essentially, we're comparing and contrasting the two. Galvanic and voltaic cells. So this is a battery. The electrolytic is not a battery. So we're asking first, is this thermodynamically favorable? Yes. My E cell is positive, and my delta G, going back to Gibbs free energy, is negative. Whereas in electrolytic, this is not thermodynamically favorable. That's a negative E cell value and a positive delta G. Typically, you'll see 2 vessels for this one. For electrolytic, you might see 1. Maybe you might see 2 test tubes. 1 year they had for a voltaic and galvanic cell, I remember a free response where they had I think it was a hearing aid. They showed the cells here and here. So this was one essentially like part of the electrode. This was another one, and this was a salt solution. So yeah, even though this is not 2 vessels, there's 2 separate parts of this. So the galvanic or voltaic cell does require a salt bridge versus the electrolytic does not. The battery, the galvanic or voltaic cell does not need a battery, but the electrolytic does. So, one thing I forgot to mention. It converts chemical energy to electrical because we are producing electricity as a result of the electrons being gained or lost from atoms. Versus electrolytic, this is starting out with an electrical to chemical, meaning you start out with a battery and then that made something gain or lose electrons. Oxidation occurs at the anode for both. That's a constant. So remember anox. Reduction occurs at the cathode for both. So red cat. Cations flow to the cathode. And this is dealing with a salt bridge, so we won't have a salt bridge for electrolytic. The anions flow to the anode. And again, this is just for the salt bridge. I'm going to put that here, salt bridge. And salt bridge here. Do you see why they're called anodes and cathodes, by the way? And then overall, electrons flow from the anode to the cathode. And that happens for both. And then this is through the wires. I'm going to kind of put that here for both. Through the wires. Cool. You could do a sketch down here, but we've kind of already taken care of our 2 sketches over there. So remember, this is just the foundation. Make sure you watch those AP Classroom videos to help you with the rest. Have a wonderful, wonderful day, and I will see you later. Take care.